Using dynamic linking, we can have a very interesting application, runtime interpositioning. So let me introduce how it works. Runtime interpositioning means that interpositioning here means providing some function, adding some function in between the target program and library in order to monitor or in order to intercept the behavior of the library function. Here's some story. So library interpositioning is a powerful technique that allow programmers to intercept some function execution. So this is a powerful method for debugging, and also many useful information can be extracted through this library interpositioning library interpositioning technique, I let her say. And interpositioning can be implemented in a different layer. So for example, it can be applied at the compile time and link time and also runtime. And in this video lecture, we will see case for loading time or runtime. More exactly speaking, runtime library interpositioning we will see. Library interpositioning can be utilized for security reason, for sandboxing, or by intercepting some library to the sensitive system call. We can block certain applications attempts to invoke some important system call through library interpositioning. And in order to fix a bug, we can use it. So for example, in 2014, Facebook engineer debugged a serious problem that they observe in the iPhone app. And for fixing this problem, they need to rebuild the app, and it takes many hours for actually fixing this problem. But they make a very quick patch by utilizing this library interpositioning, so that they can mitigate the risk of the security problem, risk of the security problem, and make the application smoothly work with this technique. So this type of the debugging can be easily done when we have library interpositioning, and the technique is very intuitive. So let's check this example. This example has analog memory allocation and free. And what if we want to trace what's the address that is allocated by analog function call when program get executed? Maybe we are interested in debugging the memory bugs, so that we want to check all the pointer or the address to the newly allocated heap objects that ever allocated in a program. How can we achieve that? What if we can replace actual analog such that we can print out the result of the analog in all the time when it gets executed? If we can replace analog with a different function, then at that function we can add some monitoring scheme in addition. Then we can extract the information of the program behavior by using those interpositioned function. So for example, here, let's check this code. So this is a target program. So we don't want to touch this program at all. We just use the target program as it is. We don't want to touch that. Just let it as it is. Then the program will be built, and it will looking for the definition of the analog at the linking time. At that moment, instead of providing the system's analog definition, we, as a debugger or the engineers, provide a definition of the analog that has the same name as analog, but that is not analog. So for example, we are here creating our own function analog and make this program link to not to the system's analog, but to our definition of the analog. And our definition of the analog actually calls on system analog by dynamic linking. So here we looking for actual definition of the analog. So here we use RT LD next. And you can simply accept this one. This one is I think global variable, or it's a kind of a macro that indicate the current linking path, the path that looking for the library that is given as a given by the system. And from the system, we are looking for function name analog, and if there exists, it return a pointer to that analog function, which is actual function analog. But we hold that as analog P because we have an analog here. So this program will, this analog function call will be bound with this our own version. But in order to implement our own version of the analog, we need to call original analog that is given by the system. So we here refer original analog by analog P, and actually colon analog P with this given size and get the pointer and return the pointer. In that sense, this analog is a kind of a wrapper of the system analog. But in addition with this original analog behavior, we are printing out what's the address that was returned by analog to the standard output, so that we can see which address is allocated in this program throughout the execution, which will be informative information for this program's debugging. This simple situation is not that meaningful, but what if the programs are super complicated and there are multiple analogs and some memory error happens, then we want to, in order to know the memory access, memory allocation, we need to add a printf for every analog, which will be tedious, but even more, it will be impossible if there are too many analog invocation. But by providing this alternative dynamic library, shared library that is a wrapper of original analog, but printing out this information as an emission of the debugging information, then we can easily extract this information without changing anything for target program. So same way, here we are replacing free by providing wrapper free, which is written by us, but it relays this information to actual free that was found in the system library, and we here refer this actual function free as a free P and calling on it. And in addition to that, we here program to emit the pointer that actually passed to the free function. Okay, and the emission goes to the emitted information is to be collected, or it will be recorded as standard output. Okay, so if we make this alternative library, what we need to do is make them as a shared library first. So here we have a GCC, and GCC has the special features to create a system library, shared library, and these are the keywords that make the shared library. -share, -fpic, and we here provide the name should be this one, and this is the source code. You want to use the dynamic library, the library for dynamic linking. Okay, then it generate what? myanalog.so. This is a shared library. Okay, and we compile here the target program. This is the target program in ordinary manner. Nothing is changed in this target program. But what is interesting thing here is that when we execute the target program, we usually execute in this way. At the bash, we give a command that we are loading the intr. That's ordinary case. And at this loading time, the loader, the logic for initiating the program execution, it dynamically binds the actual definition of the analog from the result that was searched by the kernel. And the search starts for system directory. It usually is a user lib, or we can change the system directory by build option. And what is more interestingly, we can change the target of the binding by execution command for setting up some environment variable in this way. So at the bash, if we are defining LD preload, this is a special environment variable that indicates the first place the library was searched for. And we here give it as our own library, my_malloc. And while setting that under this option, if we execute the instr, if we put this one in front of the execution command, then what's happened is that in this execution, before checking the system directory, it first checks on this library for malloc and free, and here binding happens, so that this one will call on this function. This free will call on this function, so that we are here interpositioning our own function in between the target program and actual malloc library. Yes, this is a runtime interpositioning technique, and this is super useful for monitoring what's happening inside of the program execution, and also we can change the behavior as we want by overriding the library function's behavior. So let's see more cases of this runtime interpositioning with our own example. So let me put our own code example on the front. Okay. This is, you can find this example under the linking interposition. Okay. So I here brought two examples for runtime interpositioning. Let's check first the example. First example consists of the myrand and test1, and we can build the whole program by calling make. And this is the contents of the make. Test is the target program, so it's simply built with a simple option. And this is myrand is a random function library that I want to position between the target program and an actual random. So I make this myrand.c as a shared library, and here I use option -share fpick. This is something you need to memorize and use. Okay, and here -ldl, and this is a kind of package. So this is a kind of a convention. So if we use this option, then we can have a shared library. So we have another example for that we have other source code, but let me here focus on test1 and myrand. So let's check the target program code first. Test1, here it generates 10 times random number and print the result to the screen. And in order to generate different random number whenever every time it get execution, it get executed. So here I set the random seed from timer value. As it is configured in this way now, then the current millisecond is given as a seed to the random, so that every time the program will get executed, it'll be very likely to have a different seed number, so that the generated sequence of the number will have a different pattern. So if I execute test1, then it generates some random integer number every time as I execute this program. This is test number 1. Okay, but suppose that you wanna, so this is a simple program, but what if you have a complicated program and it has some random number generation, and its behavior is determined by random number in some sense, but your program has an error. So only under certain condition of the random number, the error appears. So you don't want to make this the random number for debugging purpose. At the moment of the debugging, if the random number actually generate different number whenever get executed, then you have a less reproducibility in debugging. So you want to here control such that random number generate pretty deterministic value, even though it is programmed to get a seed from timer. So you don't want to touch anything for test number 1, but you want to control the random function's behavior such that it generates deterministic result. And we can achieve this one as a library, runtime library interpositioning. So test number 1 is as it is, but we here put create a my rand.c. This is also a convention. We need to put sharp define GNU source. And here I have created one static variable. This is a global and static variable. I think at the moment when I explain about ELF, I didn't talk about what's the effect of the static. When I put the static in front of as a keyword to the variable, then the specific location address of that variable is preserved at data section, and all the symbol will disappear. This is the important part. So let me elaborate. Do I need to? Why don't? Okay, why not? So let me give show you an example. So if I simply compile this program into a object file, so for example, what you see is that if I name all the objects under this program, then we have a counter global variable, and it is called as a b, and rand, the random function. But if I remove the static keyword in front of it, and yes, here the keyword becomes different, and this difference means that here, when it is a large b, this shared variable, this is a global variable that can be referenced by other module at the linking time. So other locatable object may refer this global variable. Because all the global variables are kind of an interface to the module. Module here means locatable object. So functions are such cases. So functions are all public functions, and also here the global variables are all public global variables for this locatable object. But if we put static keyword in front of it, then you can regard that the static, once we put the static keyword, it becomes like a private. So it get a fixed location on the data section. So afterward, the symbol itself doesn't matter, but it will be referred by absolute address, so that it becomes exclusive to this current module. So no other module can refer count if it is declared with the static keyword. Okay. Actually, that is a kind of a different story. So, but before moving on, I elaborate on that part, because a similar pattern of the declaration appear again in the other part of the this group of example. So here we have a global counter, and counter start from 0, and whenever rand function get executed, not the random number, but the current counter will be returned, and counter got incremented by every execution. Okay, so this is a kind of an alternative definition of the random function, rand function. So we here wanna attach or binds this function not to bound with the actual system's random, but here we wanna bind it with this alternative rand, which behave in a deterministic manner, which will be helpful for debugging. So if we simply execute the test number 1 by itself, then it's executing the actual rand. So in order to replace with our own example, our own alternative function, prior to this execution command, we need to put ld preload is what? My rand.so. So if you're looking for a definition of some library, before going to the system library, you first need to check this given library, and if there is a definition, you should bind it with it. That is what this ld preload environment variable indicates. Even if we execute in this manner, I don't touch anything for test number 1, but at runtime, not runtime exactly speaking, loading time, test number 1 binds with our own shared library so that we have an effect of the replacing the random function into our own version. And it changed the behavior of the target program, right? So this is a kind of useful for debugging. This is a very basic example of runtime library interpositioning. In next video, we will see one of more sophisticated example of course, runtime library interpositioning.